Hello everyone. In the previous lecture, we were discussing about the Lami's strain potential, and in the lecture prior to that, we were discussing about the Helmholtz displacement potential. Now, both the Helmholtz displacement potential and the Lami's strain potential represent the displacement vector u. So let me write this. So the Helmholtz displacement potential and the Lami's strain potential they both represent the displacement vector u in terms of first order derivatives. In terms of first order derivatives of potentials. Okay. Of course, it was true that in the case of the Helmholtz displacement potential, the displacement vector was expressed in terms of a scalar potential and a vector potential, whereas in the case of the Lami's strain potential, the displacement vector was represented in terms of a single scalar potential. But in both these cases, the commonality is that the derivatives were all first order in nature. Now, Gallerkin, he came along and said that it may be useful to represent the displacement vector. So that's what is we are going to study today, the Gallerkin potential. This is the topic of our study in this lecture. So what he said was that it will be useful to express this displacement vector not in terms of the first order derivatives of potentials, rather in terms of the second order derivatives. And you will see the consequence of this shortly. Another important thing which Gallerkin mentioned was that this representation can be done in terms of a single vector potential. So immediately you can see that there are certain important differences both with the Helmholtz and the Lami's strain potential. It was true that in the Helmholtz displacement potential, we had a vector potential, which was our capital omega, if you look back to the lecture notes there. Whereas in the case of the Lami's strain potential, there was a single scalar potential. Now, what Gallerkin said was somewhat of a mixture between the two. Okay, so he is saying that the displacement vector u will be representable in terms of a single vector potential. So the form that he gave was like this. Where this capital V vector is the vector potential, is the Gallerkin vector potential. Let me write that down. This V vector, that is the Gallerkin vector potential. Now looking at this form, it is very easy to wonder, how does one arrive at this? Is this some kind of black magic? Certainly not. Okay, and what I will do is, there is a clever way in which this particular form can be arrived at just from the initial consideration that all we want to do is to express this displacement vector in terms of second order derivatives of a vector potential. Just from that initial consideration, we can arrive at this particular form. but I'm not going to go down that route in this lecture. Rather, what I will do is something similar to what I had been doing both in the case of the Helmholtz displacement potential discussion as well as the Lamy strain potential discussion, and that is to utilize this particular form given that as it is given by Gallerkin, and to use it in the Navier-Lamy equation. Okay, so we go back to the Navier-Lamy's equation, which is lambda plus g grad div of u plus g del square u plus rho b vector. As we had been doing in the previous cases, we keep the rho b vector for now and see the consequence of keeping it. All right. So what we are going to do next is something that we simply cannot avoid. This complicated looking expression for the u vector that we have to substitute here. Okay, and please note that there is no further simplification that is immediately possible here. Okay, so we actually have to go through the algebra. All right, so let's do that. So what we have here is, so if we just substitute this for this u first, so this 1 by twice g, I'll take that out of all these operators. So that's lambda plus g by twice g grad, and now I'll actually carry out this divergence over this. Okay, so I may be skipping a little bit of steps here and there, but I'm sure you'll be able to follow along. So see, this is the first term that I have done here, this one. Please note that when I am operating this or when I'm carrying out this divergence, basically for this term, this is the divergence of the Laplacian of the v vector, and what I have done is to take the divergence inside this Laplacian in order to arrive at this term. Here I have taken the divergence on this gradient for which I am obtaining this, from which I am obtaining this Laplacian, and it turns out that this one and this one are I mean, they are the same kind of terms, and we are going to simplify this in the subsequent step. Next, for this g Laplacian of u, we have to again substitute this this entire thing here. Now this 1 by twice g with this g, so that will give us a half. So what we have here is 2 into 1 minus nu Laplacian of the Laplacian of v vector, that is the bi-harmonic operator operating on the v vector, minus we have the grad of the Laplacian of the divergence of v. So let me just discuss what I did. You see, this Laplacian is operating on this entire thing. The first term is taken care of by this bi-harmonic. For the second term, this is basically the Laplacian of the gradient of the divergence of v, and what I have done is to take the Laplacian inside and put the gradient outside. So that's exactly what I have done here. So I've skipped a step here. Okay, and of course I have this rho b vector term that is equal to 0. All right, this entire thing is equal to 0. Okay, now of course I can simplify this a little bit. So let me do that. Okay, so this, you note, is basically half lambda by g plus 1. This is 2 minus twice nu minus 1. These terms, this is common. So what I obtain is basically 1 minus twice nu, and this gradient, it can go inside. So what I obtain is basically gradient of the Laplacian of the divergence of the v vector. And please note that this term is kind of matching with this here. Okay, we'll see the consequence of that. Next, so this entire first term is done for. This half and this 2 cancel, so we don't need this. We just have this 1 minus nu bi-harmonic of v vector and 1 by 2 gradient of the Laplacian of the divergence of the v vector plus rho v vector is equal to 0. Now you see we have this lambda by g plus 1 term. Let us see what is actually that if we try to simplify it. Okay, so what we intend to do here is to find an expression for lambda by g plus 1. Now lambda is e nu divided by 1 plus nu 1 minus twice nu. If you do not remember this, I'd request you to go back and refer to the problem sheet on material behavior. G is e by 2 into 1 plus nu, so and we have this plus 1 here. So this 1 plus nu cancels with this 1 plus nu. This e cancels with this e. And what we are left with basically is twice nu divided by 1 minus twice nu plus 1, which is nothing but 1 minus twice nu. And this should make you particularly happy because you see this lambda by g plus 1 that is multiplied with 1 minus twice nu. So that is basically cancelling with this. So if we substitute it back here, what we are going to obtain is half grad of the Laplacian of the divergence of v vector plus 1 minus nu bi-harmonic of the v vector minus half gradient of the Laplacian of the divergence of v vector plus rho b vector is equal to 0. And of course, very nicely, this entire term cancels with this entire term. So what we are left with is, with a little bit of rewriting, transposing and dividing by 1 minus nu, we obtain this particular form. Now again you consider what happens. So see, as written, we can hope to find some possible solutions of the v vector, but things become really convenient if we again consider the rho v vector to be equal to 0, as we had been doing in the previous 2 cases of the Helmholtz displacement potential as well as the Lamy strain potential. So consider rho v vector to be equal to 0. Then we end up with del 4 v vector is equal to 0. And this again should make us particularly happy, of course with the caveat that we are working under this restriction of 0 body forces. But as far as the equation is concerned, this should make us particularly happy because this bi-harmonic equation form has been studied so much, and the solutions to this are known in very many different situations for different geometries. All right, so what is the situation? So back in the Helmholtz displacement potential, we had ended up with similar kinds of bi-harmonic equations. However, in that case, the bi-harmonic equations were of two kinds. So we had a bi-harmonic equation for the scalar potential. If we just look back at it, let me just scroll back and look at the Helmholtz displacement potential framework. Okay, so this was what we had discussed in the previous lecture, and prior to that, so this was the part where we were discussing the consequences of considering the rho b vector to be equal to 0 in the context of the Helmholtz displacement potential. And we had obtained these two equations, the #1 and the #2. You see that this was a bi-harmonic equation, this was also a bi-harmonic equation, but we had two of those things in the Helmholtz displacement potential. Now, coming back to the Gallerkin vector potential, we are obtaining a single bi-harmonic equation which encompasses our desired solution. Okay, so this is an important difference from the Helmholtz displacement potential. Okay, so you see the consequence of working or starting out with, as Gallerkin had suggested, a single vector potential. We are obtaining a single bi-harmonic equation of a vector. So this is basically actually three equations. Okay, now it is important to note that if we are working in the rectangular Cartesian coordinate system, then the different components of this v vector, we will obtain decoupled equations or decoupled bi-harmonic equations for each of the x, y, and z components of the v vector. But things are not going to be so simple, meaning to say that suppose we consider a cylindrical coordinate system or a spherical coordinate system, then the different components of the v vector, the bi-harmonic equations involving those different components, they are not going to be decoupled. Decoupled means if you are considering, so in the context of the rectangular Cartesian coordinate system, if you are considering the x component, the bi-harmonic equation involving the x component will only and only involve the x component equation. It will not have any influence from the y and z components. Similarly for the y and z components themselves. So they are independent from each other. But in the case of the cylindrical or the spherical coordinate system, suppose you consider the cylindrical. So if you start out by writing if you intend to write the bi-harmonic equation by taking the r component of this, you will see that there will be influences from the other components. Okay, so that's what is meant by the absence of decoupling in the cylindrical or the spherical coordinate system. All right, so that is a complication that we have to deal with. Another important note is that this Gallerkin vector potential, at least historically, it was foreshadowed by another kind of a potential which was referred to as the Love's potential. So Love, A.E.H. Love, was a famous mechanician. He was also the author of a very famous book which is widely used, called the Mathematical Theory of Elasticity. And there was a time when people used to jokingly say that in order to study elasticity, all you need is love. But that book has been, it's still referred to, but that has been, well, succeeded by more modern versions of elasticity books. Anyway, so that famous Love, he also gave a potential, a displacement potential, and his motivation was to study various kinds of axisymmetric problems. All right, and it turns out that the Love's potential is a special case of this Gallerkin vector potential. Now, I mention this because uh, ultimately what we are building up to is to be able to develop a framework so that we'll be able to solve the Kelvin's problem. And if you refer to the textbook, uh, to our textbook by Martin Sard, you will see that the solution to the Kelvin's problem has been given stemming from this Gallerkin potential, and the way it has been given is that you have been supplied with a particular form for this V vector, and you have been asked to basically check out that it satisfies the conditions for the Kelvin's problem. We will be taking a slightly different route, and for that we'll discuss another kind of displacement potential called the Popkovich-Neubert uh, representation in the next lecture. But what I want to say is that the Kelvin's problem can indeed be solved through this kind of a representation or displacement potential. And there are other problems also which can be solved by this Gallerkin potential, but a more modern treatment is possible through the Popkovich-Neubert representation, which we'll discuss in the next lecture. All right. With that, I end this lecture. Thank you very much.